Hello everyone. Welcome to AIM 408, Interpretability and Explainability in Machine Learning. My name is Vikrant Kalia, Senior Solutions Architect with AWS. Before we dig into the agenda, let me clarify a few terms I will be using in this session. Explainable AI or XAI refers to methods and techniques used in machine learning to explain machine learning reasoning to humans. This is in contrast to black box machine learning, where even the designer of the system doesn't know why a machine learning solution arrived at a specific outcome. Now, the technical problem or challenge of explaining machine learning reasoning to humans is sometimes called interpretability and sometimes called explainability. There is no formal consensus in the community as to what is the fine line between interpretability and explainability. People use it interchangeably. So feel free to use whichever you like or whichever suits your purpose. There is no formal definition as to this interpretability should be used in the context when we are observing cause and effect or when we are using explainability when we are talking about deep learning systems. In this session, I would be using explainability to refer to the broader ecosystem of methods and techniques that are used to explain machine learning reasoning to humans. In terms of agenda, I will talk about why explainability is important. We will talk about different ways in which we can categorize explainability methods, and we will list some of the methods that are popular in explainability. But most of the session would be focused on one specific method called SHAP, and we will also go into the science and maths behind SHAP method, and towards the end, I will have a short demo of Amazon SageMaker Clarify, a machine learning capability for explainability that we have added to Amazon SageMaker. So why explainability? There are two dimensions to machine learning models. As you can see on the graph here, one is accuracy and the other one is explainability. We use loss function as an indicator for model accuracy, and that works very well, but loss function or model accuracy doesn't explain how fair or responsible our machine learning model is. You cannot trust the machine learning model prediction just based on the accuracy of the model. We need a second dimension, and that is where explainability comes into picture. Explainability is important to establish trust between humans and machine learning systems. It is also important or becoming important because of increasing regulatory compliance around right to explanation. In 2018, GDPR Act was enacted, and we started talking about the privacy of the data, but there is a less popular article in GDPR that talks about right to explanation. Now, right to explanation is only defined in principle for GDPR because it is precautionary, but there are countries like Singapore that are not only defining right to explanation in principle, but are also using or have developed a framework for enterprise companies to adopt explainability into machine learning systems. The interesting part is accuracy and explainability, as you can see on the graph here, are negatively correlated. What it means is that on the top left, you will see machine learning models like rule-based and logistic regression, which have low to moderate accuracy, but have high intrinsic explainability built into it. And on the other hand, on the bottom right, you will see complex models like support vector machines and neural networks, which have very high accuracy, which is desired, but are almost black box and are not explainable. So with that understanding, let us try to see what machine learning methods or explainability can do to a specific customer scenario. We understand explainability is important, and let's try to develop an intuition around a specific business scenario where it can prove to be very helpful. Take, for example, you are traveling from city A to city B. In city B, you want to buy a bottle of water. You try to make a payment with your credit card and it was declined. You tried again, it was declined again. And you were annoyed. You called the card services customer care to see what's wrong with your card, why it was declined. The customer care rep can see that, okay, your specific payment was tagged as fraudulent with a 60% probability, but that is not a good enough explanation for you because it doesn't help you in any way. Maybe there was a method or a technique that can take that 60% probability of fraud and break it down by its individual components. And in this specific scenario that you see here, there are three inputs that factored into the payment being tagged as fraudulent. And the topmost, that is inconsistency with the past activity, has the highest weightage. And that alone influenced the payment to be tagged as fraudulent. Now, this is a very helpful explanation. The customer care rep can share this information with the customer, and maybe in the future he can set up a travel alert and avoid this situation. This is the type of applications that we see for explainability that are very useful. In terms of what are different explainability methods and how they are categorized, before going into specific methods, let's talk about how the methods are categorized. Explainability methods, in one way, can be categorized based on the scope. We can have local scope or a global scope. Local scope means something that we were trying to do in the previous example, come up with an explanation for a specific credit card transaction to identify why it was declined, why it was tagged as fraudulent. That is local scope. But maybe data scientists and machine learning engineers are sometimes interested in learning overall, across multiple examples, which particular features contribute the most to the model prediction score. And that is where we take into account the global scope, and we usually use the averages across the training or the validation examples. The other dimensions that can be used to categorize machine explainability methods is methods could be intrinsic. What it means is that by the nature or the way the information is represented inside the models, that can be used to explain or decode the cause and effect observed in the system. Now, this type of methods are model specific because they take into account the information representation. On the other hand, we have methods where we don't care about explainability until at the time of the model training. And after the model training, we try to come up with a point of view to explain the machine learning reasoning behind the predictions made by that model. And these models are called post hoc. And we are going to focus on post hoc models only in this session. Let us double click on post hoc and try to see what are some of the popular methods that falls under different categories. So we are just focusing on the post hoc, and we can see that post hoc can do both local and global predictions, and under individual category, we can have model specific and model agnostic. On the left, you see methods like integrated gradients, tree feature contribution, SABAS, but we are not going to go through each of them. The focus of this session is just to see how one particular method that is becoming very popular, that gives consistent result and is backed by a good theory, we are going to talk about it, and it's called SHAP. It's important to understand theory behind SHAP because that is the foundation for the consistent results or the popularity of the SHAP. In next few slides, I would be talking about theory behind SHAP and the maths behind the SHAP, how actually the Shapley values are derived. So Shapley value is a concept in cooperative game theory. It was introduced by Lloyd Shapley in 1951. Lloyd Shapley was awarded a Nobel Prize for Economics in 2012. Let us try to understand in what situations we can apply Shapley values and try to extrapolate it to apply to machine learning system later on. Let us take an example of a ride share. Let us say Grace, Bob, and Alex on Friday evening met at a bar. They had a good conversation, and during the conversation, they realized they all are headed in the same direction. And they were excited they can travel together and save on the fare. But the problem is that they were traveling unequal distances. Now, what is the fair way to divide the fare if they are traveling unequal distance? And that is a problem. Now, Shapley value is the only solution that gives you the fairest solution for this type of scenario. What do I have to do to calculate the fare using Shapley values? Let us try to translate this particular problem statement into the constructs defined by Shapley values. So we will assume ride share is a game. The riders are the player. The miles traveled by individual rider is the contribution of individual player, and the total reward is the total taxi fare. The problem statement we are trying to solve is, given the contribution of individual players, what is the total reward or the fare that they should contribute to the final reward? And these are the type of problems that can be solved with the Shapley values. Now, Shapley values is the is the only solution that gives you the fairest possible solution because it is backed by a solid theory. Let's try to understand the axioms behind the Shapley values theory. In order to understand the properties of Shapley values, let us assume another fictitious company example. Let us say there is a company of 10 employees, and that company makes a profit, and all the profit is distributed back to the employees based on their contribution. Assuming this is the scenario, let us try to understand efficiency. When we talk about efficiency, what it means is that bonuses add up to the total profit, and the bonuses are based on the contribution of individual employees. And this is one of the important properties that distinguish Shapley values from other methods. Then there is a concept of null and dummy. What it means is that if there is a no contribution, maybe the employee was on a sabbatical for a year, no contribution from employee, no bonus. Same for symmetry. Equal contribution, equal bonus. Two employees contributing equally should get equal bonus. And the last one is the linearity property, which basically means bonus from different departments add up to the total company bonus. This is a little bit important because sometimes what we observe is, especially in machine learning system, the finest possible granular grain or the feature or the item is not accounted, and we are interested in more high-level features. So we try to group them into high-level features. The principle of linearity apply even in terms of high-level features. Take, for example, pixels. You can combine the pixels into group of pixels. It becomes a superpixel, and superpixel becomes the feature set for you. And you can sum up the contribution of all the superpixels to calculate the total contribution of that particular superpixel at the machine learning model level, and you can aggregate contribution of all the pixels, and they will all sum up to the total final score provided by the machine learning model. Linearity and efficiency are very important properties and makes Shapley values unique. So far we have spoken about general situations, about the theory, to understand and develop more intuition about Shapley values. How do we calculate Shapley values for an individual player? What we do is that assume Grace, Bob, and Alex are playing the game of the rideshare. In this example, we will try to come up with the subset. The subsets could be Bob and Alex traveling together, Alex and Grace traveling together, or all three traveling together. And these subsets are called correlations. What we will do is that we will take one correlation, and if we want to derive the marginal contribution of Alex for a specific correlation, we will try to calculate the reward. We will try to calculate the contribution with and without Alex, and that difference will give me the marginal contribution of Alex in a specific correlation. And then I will aggregate the sum of Alex's marginal contribution from all the correlations and try to get an average across all the examples. This will give me the Shapley value of Alex in a rideshare game. This is how we do the maths for Shapley values. I know it was mouthful. You don't have to worry about actually implementing or programming these complex formulas. This is already done, and we will talk about specific implementations that are used in explainability that already takes care of it. Now the problem is, how do we translate this Shapley value concept to machine learning? It's very simple. All you have to do is, you have to take the same constructs of the game and apply them or translate them to the machine learning world. Your game becomes the model, your players becomes the features, your subset of players becomes the subset of features, your specific player becomes specific feature, your instance being explained, a specific example remains the same. And this is a simple translation. This mapping is all you need to translate Shapley values or to apply Shapley values to machine learning problem. How about the maths? Even the maths remains the same. All you have to do is just the representation becomes different, the games becomes model, and player becomes feature. That's it. So where is the problem? The complexity or the problem is is in the number of the players that are in the game in machine learning world. In the ride share example, I was only talking about 3 players, but in machine learning world, we talk about thousands of features, which are basically thousands of players, and forming correlations among them, and calculating the marginal contribution and then aggregating and taking the average across will convert this problem into an exponential time problem. And that is the problem that makes implementation of Shapley values in machine learning complex. And then there is another problem. In order to calculate marginal contribution of a specific feature, we have to calculate the contribution with and without. We have to take the correlation and calculate the marginal contribution with and without the feature. How do we represent or simulate that missing feature? This is especially a challenging problem. It's not so much of a problem in NLP and computer vision. Maybe you can use black image as the base image to simulate the missing values. But in tabular data, it's a big challenge. There is no specific prescriptive guidance on this one. We call it baseline, but there are few things that we will discuss that can help you with it. So how do we solve it? So open source SHAP implementation implemented a kernel and took into account the exponential time problem, and the way it solved is, it basically, instead of calculating the marginal contribution across all the correlations, it calculates it across some limited number of subsets or correlations. So it doesn't give you the exact Shapley value for a feature, but it gives you the approximate value. Now, the art and science here is that if you take 2 less subsets or correlations into your calculation, your values may not have a practical use. They may deviate and may not be close to the actual one. And if you try to take into account more correlations, then you're adding the computational complexity. This is the fine balance that open source SHAP implementation made and came up with this default set of 2 to the power 2 into modulo m plus 2048 subsets that are used to derive the approximate value. Now, this is step 1 of solving this problem, but there is further opportunity to improve on this particular solution, and we will talk about this the improved version when we get to the AWS services for explainability. Now, there is another problem. How do we simulate the missing values in the tabular data? What we call these missing values as the baseline. We need to define the baseline to represent the missing values. Sometimes we can use training sets. Sometimes we use median of the data set. K-means representatives. I don't have a prescriptive example for you, but let's assume that we will use training set as the baseline in the examples, and I will demonstrate it in the demo, how to specify the baselines when we are trying to kick off a explainability job. So I'm switching the gears here, and so far I've spoken about the theoretical aspect of SHAP and the open source SHAP implementation, and how SHAP solves the computational problem by taking into account only the approximation and not the real value. Amazon SageMaker Clarify is extending and making it further simple for machine learning engineers and data scientists to build explainability into machine learning development life cycles. And Clarify is a capability that we have added into the Amazon SageMaker. It does 6 things. The top 2 things are not relevant for this session because they're more focused on the bias. It can help you detect bias in data. It can help you detect bias in the trained model. The bottom 4 are what we will focus on. The bottom 4 basically means this service can give you local explanation. It can give you the global explanation. It can also help you detect drift in the feature importance over time. And in case you are operating in one of the industries that requires right to explanation, you can also generate reports that can be shared with auditor to comply with right to explanation guidelines. Now, that is the high-level capabilities of Amazon SageMaker Clarify that addresses both bias and explainability. Let's try to dig in how under the hood it works, or what are the aspects of technology that it tries to simplify. The first thing that we did was we took the SHAP algorithm and we containerized it. We packaged it into a container and we optimized it further. and then we made it programmable through SageMaker SDK. So if machine learning engineers and data scientists are already using SageMaker SDK, it will seem very familiar to them the way they launch the training job. It will be the same experience that they can launch the explainability analysis job as well. And we will demonstrate it in the demo. Now, another thing that we have optimized is data scientist and machine learning engineer time needs to be optimized. So there is an opportunity to parallelize the explainability jobs to make it run faster. And the way we did is you can specify more than one SageMaker instances to run your explainability jobs, and we have parallelized it using Apache Spark. This lets you complete the job faster and save the to improve the productivity of data scientists. They don't have to wait long for their explainability results to come back. And the bottom two points that you see here for Clarify, they're more about, we have integrated, Clarify is not a service that lives in just step one of machine learning or during the model debugging. It lives throughout the model development lifecycle in different stages. You can use it from within the Amazon SageMaker Studio, or you can also use it to see how the model, the feature importance or attributes is changing for a deployed model. And we provide charts for both model monitor and from within the studio that can be accessed by data scientists to understand their model better. Now, how do we take all this and apply it to the real world problem? One of the AWS customers, Zopa, which is a UK-based digital bank and peer-to-peer lender, wanted to apply explainability capability to fraud detection to earn trust of their internal and external stakeholders. And they used Amazon SageMaker Clarify and can now produce model explanations more quickly and seamlessly. I hope after listening through this session, you would try Amazon SageMaker Clarify and would apply it to more exciting use cases. So with that, we will jump into the demo. In the demo, I'm using the German credit dataset. This dataset has attributes. These attributes are like age, the length of the credit history, the gender, the foreign origin of the requester. And the label here is, or the prediction we want to make is, whether this particular requester has a high risk, falls into the high risk category or low risk category. So it's either 0 or 1, a binary classification based on the model attributes. I've already trained a model, an XGBoost model that I'm using in this particular example. And the problem that I'm trying to solve is I want to come up with an explanation of what is driving, which particular inputs or factors are contributing the most to the model, to the classification. I would be using Amazon SageMaker Studio to demonstrate this example, and there are two parts to the demo. In part one, I would be using Jupyter Notebook and SageMaker SDK to start a Amazon SageMaker Clarify job, and then I will pull the results from a destination, bring it into the notebook and try to project some results. And then the second part of the demo is more focused on model monitoring. Amazon SageMaker Clarify integrates with Model Monitor. It leverages and integrates well with Model Monitor, and you can add charts to your Model Monitor that shows change in feature attribution over time. So let's start with demo one. I'm in Amazon SageMaker Studio. I'm using the German credit dataset. I already have a trained model. I'm using the analyzer processing job Jupyter Notebook. In this notebook, first thing I'm going to do is I will specify 3 different inputs that are required to start the processing job. The first is the analyzer, the analysis config, which basically says I want a SHAP explanation for my model. I will provide a path to the data set, and then I will specify a destination where my results will be published. And I hit run, and behind the scene, what Clarify is doing it will pull in the optimized SHAP algorithm container and will use the baseline set, will deploy a shadow model in the same VPC to do the inference, and then will push back the results into the destination path. Now, once the results are available, you can see these results. This is how they look. I can pull it into the Jupyter notebook and see how they're structured as a JSON. But that is not very intuitive. But on top, what you would like to do is you would like to draw charts using this data. And you can do it for bias and explainability. I'm going to skip the bias part. So we will try to analyze the feature importance, and this is the last chart is what showed me the feature importance. The next part of the demo that you see here is about how to track model monitoring. So in this case, I will go to components and registries, go to endpoints, and I will see my model being deployed here that says German XGB. I will pull that model, and again, on the top you see there are 5 entries. I will click on model explainability, and then it will take me to the place where I can add charts. The first chart that I'm adding here is change in the top 10 features. I'll try to read in all the predictions made in a specified time, and from there I will try to see what are the top 10 features that contributed to the predictions in that duration. And let's try to do another chart this time. Maybe I'm interested in feature attribution changes across a specific timeline, maybe a week, and see how it is varying. So in this example, I took the duration as 1 week, and I'm trying to see maturity months and how the feature attribution is fluctuating within that 1 week window. And you can do it for other features as well, such as loan amount. So I showed you 2 places where you can use Amazon SageMaker Clarify, and you can see how simple it is for data scientists and machine learning to use SageMaker Clarify from within Amazon SageMaker, and also from within SageMaker Studio to monitor the feature importance or feature attribution of a deployed model. With that, it brings us to the end of the demo and to the end of this session. Thank you all for listening in, and please complete the session survey. Hope you have a good rest of the day. Thank you.